the moment coefficient about the center of gravity can be described by a straight line with respect to the angle of attack. So this can be written as Cm0 plus Cm alpha alpha, where, as mentioned many times before, this Cm alpha is the slope of the moment coefficient with respect to the angle of attack. Both Cm0 and Cm alpha contain contributions from different aircraft components. For instance, Cm0 comes from the wing. There is Cm0 from the fuselage, and there is Cm0 from the tail. And the Cm0 due to tail is tail efficiency factor, horizontal tail volume ratio, lift slope of the tail, times the downwash at zero angle of attack plus the wing setting angle minus the tail setting angle. And similarly, the slope of the moment coefficient also has contributions from wing, tail, and fuselage. The wing contribution is CL alpha W x CG over C minus x AC over C. Moment coefficient slope due to tail is eta times the tail volume ratio times CL alpha T 1 minus d epsilon d alpha. So what we can see here is that the stability is significantly affected by the center of gravity. Right, it is affected by the center of gravity, and the center of gravity can change during the flight as the payload moves inside the fuselage. As the amount of fuel changes in the fuel tank, the center of gravity of the aircraft can shift. So we would like to know what is the range in which we can allow this center of gravity to shift. Okay, because the shift in the center of gravity is going to change the stability characteristics, because we know that the aircraft is going to be longitudinally statically stable only when Cm alpha is going to be less than 0, right? So this is the condition for longitudinal static stability. And then Cm alpha equals to 0 is the condition for neutral stability. And Cm alpha greater than 0 is the condition for instability, right? So this will make the aircraft statically unstable. So we would like to know what is the range of xCg which will give us this condition. Okay, so to find that, we need to determine the value of xCg which will make Cm alpha equals to 0, and that value of xCg which makes Cm alpha equals to 0 is known as the neutral point. So the neutral point is the xCg location where Cm alpha equals to 0. So this gives us another perspective on thinking about stability. So we can also think about stability in terms of the neutral point location, as it will become more clear in a little bit. First of all, let's find an equation for the neutral point. So that you can find by setting Cm alpha equals to 0. So by definition, this xCg, this center of gravity location, is the neutral point, right? So we can write xnp over c. So neutral point is a center of gravity location, is equal to xac. So I'm just going to copy the right hand side from the previous step, Cm alpha f divided by Cl alpha w plus eta vh Cl alpha t divided by Cl alpha w 1 minus d epsilon d alpha. So this is the equation for the neutral point. If the center of gravity location, if xcg is greater than the neutral point location, then this will make Cm alpha positive, and that means the aircraft will be statically unstable. When the center of gravity is equal to the neutral point, this will make Cm alpha equal to 0, and that will make the aircraft neutrally stable. And when the center of gravity is located before the neutral point, right? So when the center of gravity is closer to the nose, that will make the aircraft statically stable. So that will make the Cm alpha negative, and that will make the aircraft statically stable. So the location of the center of gravity relative to the neutral point also becomes another way of thinking about static stability. So for this reason, there is another parameter which is defined and used sometimes, okay, which is called the static margin. So static margin, what do we mean by static margin? Static margin is defined as xnp over c minus xcg over c. So let's apply these conditions to the definition of static margin. When xcg is greater than xnp, the aircraft is statically unstable. That means when the static margin is negative, the aircraft is statically unstable. Okay, so negative static margin makes the aircraft statically unstable. When xcg is equal to xnp, static margin is equal to 0. So 0 static margin means neutral stability. And when xcg is less than xnp, that means the static margin is positive. So positive static margin leads to statically stable, static stability. Yeah, okay, you can put boxes around these as you prefer. Okay, so static margin is basically another way of defining the stability criteria. But primarily all these interpretations arise from the concept of moment slope, right? So if the moment slope is negative, then there's going to be a restoring force which will make the aircraft stable. If it is positive, then there is no restoring force actually, so that will make the aircraft unstable. Okay, and if it is 0, then there is basically no force acting, so it will make the aircraft neutrally stable. Okay, so here is the problem statement. It says consider a model of a wing body shape mounted in a wind tunnel. So wing body shape basically means an aircraft, a simplified aircraft, maybe some parts are missing. The flow conditions in the test section are standard sea level properties with velocity of 100 meters per second. So this means density is equal to 1.225 kg per meter cube, because it says standard sea level properties. Velocity is equal to 100 meter per second. Okay, velocity. The wing area and chord are 1.5 meter square and 0.45 meter respectively. So area of the wing is equal to 1.5 meter square and chord is equal to 0.45 meter. So it says chord here, you can assume that this is the mean wing aerodynamic chord. Using the wind tunnel force and moment measuring balance, just like what we have in our lab, the moment about the center of gravity when the lift is 0 is found to be minus 12.4 Newton meter. Okay. So what it, all right, when the lift is 0. So when CL equals to 0, not CL, it just says lift. It doesn't say lift coefficient. It just says moment. It does not say moment coefficient. So let's not get ahead of ourselves. Okay, so moment is equal to minus 12.4 Newton meter when CL equals to 0. Again, when lift equals to 0. When lift equals to 0. So this makes me also imagine the moment versus lift, or CL versus CM. Okay, so basically it is giving you some information on a data in this plot. So when lift equals to 0, moment equals to minus 12.4. So let's say this is minus 12.4 Newton meter. When the model is pitched to another angle of attack, now it doesn't say which angle of attack, the lift and moment about the center of gravity are measured to be. So there is some alpha, and at that alpha, the lift is equal to 3675 Newton, and moment equals to 20.67 Newton. So again, if I try to represent this in moment versus lift, as okay, so I have the pair of lift and moment. So lift is 3675. Okay, so let's say this is that 3675. So at that value of lift, the moment is 20.67. So let's imagine that this is where 20.67 is, right? So this is your 3675, and moment is 20.67. I'm just going to connect them with a straight line. All right. Assume that a horizontal tail with no elevator is added to this model. Okay, so it was just a wing body shape. It had a body, it had a wing. Now, in addition to that, now it talks about adding a horizontal tail. Okay, so the horizontal tail is added. With no elevator is added to this model. The distance from the airplane's center of gravity to the tail's aerodynamic center is 1 meter. So the distance between CG and AC of the tail, that means LT, the tail moment arm, is equal to 1 meter. Distance from the airplane's center of gravity to the tail's aerodynamic center is 1 meter. The area of the tail is 0.4 meter square. So area of the tail is 0.4 meter square, and the tail setting angle is 2 degrees. So that is IT. IT is equal to 2 degrees. The lift slope of the tail is 0.12 per degree. CL alpha T is equal to 0.12 per degree. From experimental measurement, E0, that is the downwash at 0 angle of attack, is 0. So E0 equals to 0, and the slope of downwash equals to 0.47. Okay, 0.47. The absolute angle of attack of the model is 5 degrees, and the lift at this angle of attack is 4134 Newton. So when the absolute angle of attack is 5 degrees, the lift is equal to 4134 Newton. Okay. Calculate the neutral point and static margin if h equals to 0.26. So here h is xcg over c. Okay, so xcg over c equals to 0.26, and you should find the neutral point xnp over c, and you should find the static margin. Static margin is just the difference between the neutral point and the center of gravity, right? So that's pretty straightforward. If you know the two, then as long as you know the definition of static margin, you can find the difference between xnp and xc. The equation for neutral point that we just wrote is xac over c minus cm alpha f over cl alpha w plus the tail efficiency factor, tail volume ratio, cl alpha t divided by cl alpha w, 1 minus d epsilon d alpha. Now, in this problem, we are going to ignore the fuselage contribution. It has already been included in the wing contribution. Okay, so basically, ignore this term. Okay, neglect. So only focus on the two terms. Okay, this XAC term comes from the wing contribution, and the last term comes from the tail contribution. Now, the tail efficiency factor, if it is not given to you, then it is safe to assume that it is equal to 1, because even if we do not make that assumption, it only varies typically between 0.8 and 1.2. So eta equals to 1 is a fair assumption in most general cases. So eta equals to 1. Now the tail volume ratio, that is equal to ST times LT divided by SC. This is by definition, as we have already discussed in the past. So this is equal to, okay, the area of the tail, which is given to us as 0.4 meters square, times LT, given as 1 meter, divided by the wing area, 1.5, times the chord of the wing, 0.45. So I need to find CL alpha W, and I need to find this, correct? These are the two unknowns which need to be figured out before we can determine the value of the location of neutral point. So CL alpha W can be found, I think, from this information. But we have to convert the lift into lift coefficient. So let's actually first represent this in a sketch so that we have a very clear understanding of what is going on here. So even before I make that sketch, let me convert the lift into lift coefficient. So CL is equal to lift divided by half rho v square s. Lift is 4134 Newton. Half times density is 1.225 times velocity, given 100 meters per second, so 100 square, times the wing area, 1.5 meters square. So what is the value of CL that we get here? Okay, so come back to this information. We have CL equals to 0.45. When alpha absolute is 5 degrees, we need to understand what is alpha absolute. Alpha absolute is the angle which is measured from zero lift. Okay, so let's say this is CL versus alpha. Now, absolute angle of attack is measured from this point. So from here, this distance is 5 degrees. And when the absolute angle of attack is 5 degrees, lift coefficient is 0.45. 0.45. So if you want to calculate the slope, we want the CL alpha T. No, wait, we want CL alpha W. CL alpha T is given to us. CL alpha W, then we should obviously divide this by this. Okay, so 0.45 divided by 5. So this gives us CL alpha W equals to 0.45 divided by 5. I think this is going to be 0.09, right? 0.09 per degree. Now this CL alpha T is in terms of degrees, CL alpha W is in terms of degrees. So no need to convert into radians. They will cancel out. The units will cancel out. The only unknown here is XAC. How do we handle that? Large contribution. I'm also going to set this equal to 0. You know why? Because the information that is given about the moment is when the tail was not added. You see, just read the first part again. Consider a model of wing body shape mounted in a wind tunnel. The flow conditions in the test section are standard sea level properties with a velocity of 100 meters per second. The wing area and chord are 0.5 meters square and 0.45 meters respectively. Using the wind tunnel force and moment measuring balance, the moment about the center of gravity when the lift is 0 is found to be this. When the model is pitched to another angle of attack, the lift and moment about the center of gravity are measured to be 3675 and 20.67 Newton respectively. So this measurement of moment versus lift is obtained without adding the tail. The tail is only added later on. The information that is given regarding moment versus lift is the model without the tail. So initially the model was like this, and they made some experimental measurements. And later on they added a tail, and then they want us to calculate where is the neutral point when the tail is added. Which means if I want to use this information of moment as a function of lift, and if I want to feed that information into this equation, then does that not mean I can just ignore this part? Because that information does not it does not assume that the tail is added. The tail is added only later on. Okay, so I'm going to just use this as the equation for CM alpha in order to find XAC. 20.67 minus 12.4 divided by change in lift. That's going to be 3675, right? 3675. So I'm going to write dm dl is equal to d m divided by half rho v square sc over L divided by half rho v square sc, right? So I'm just dividing the numerator and denominator by half rho v square sc. This is equal to d. Okay, but this is not what we want. We want this. So we need to keep going now. So, but we have run out of space. Where can I continue this process? Okay, so this is a number, right? We got this number, isn't it? This is same as DMDL. DMDL became this. So we have that number 0.00899. So we have 0.00899 is equal to C DCM D alpha DCL. So I can now get DCM D alpha equals to 0.00899 divided by C times DCL D alpha. And we have C. DCL D alpha we calculated, right? 0.09 degrees. So we can find this DCM D alpha. So after you find DCM D alpha, you will make a substitution here. And you can calculate XAC. Then you come back here. You know the value of XAC over C. We have discussed these other terms and how they should be calculated. So everything here is a number which is known, and you can find the value of X and P over C. And then that is one of the answers which is required to be found. Static margin is just the difference between the neutral point location and the center of gravity location.